So this is continuing on from 2.1 where we talked about benzene rings yesterday. The functional groups here is what we're going to talk about today, and some different types of naming, going off of our alkenes, alkanes, and alkynes. So it says a functional group. So a functional group is an arrangement of single atoms or group of atoms other than carbon or hydrogen attached to an organic molecule. Some examples of functional groups that we're going to cover will be halogenated hydrocarbons, alcohols, carboxylic acids, and esters. And just to remind you, if you go to your data booklet, you can see all of those there. So they give you an example of them, and we'll go through how to name all of those. Okay? So the first one is halogenated hydrocarbons. So these are regular hydrocarbons where the hydrogens have been substituted for an element from the halogens. So we could have a chlorine, a fluorine, a bromine, or an iodine. So just to give you an example of what that might look like. Let's say all of those lines would go to an H. And then one of them would be a halogen. So let's say this one on the end is F. So that F is a halogen, and that is fluorine. So that is how you would have a halogenated hydrocarbon. So how we name them. So it says we name the parent chain just like we did before. So alkanes, alkenes, and alkynes. Then find all the side chains just like before. So your methyls and ethyls and all of that stuff. Then for halogens, you're going to name them this way. So if you have a F, you're going to say fluoro. Chlorine is chloro. Iodine is iodo. And bromine is bromo. So if one halogen appears more than once, use the appropriate prefix, di, tri, tetra, all of those. Number your carbons to have the functional groups on the lowest. So you always want to have your F or your Cl or your I or Br on the lowest number, just like you did with branches. And if there are double or triple bonds, the bonds take priority. So fluorines and all that stuff don't take priority over your double bonds and triple bonds. So if we're just thinking about priority in numbers, it would go bonds, then functional groups, and then branches. Okay. So you would always want to know where keep the number lowest for the bonds, then the functional groups, then the branches. That's the order of importance. So here's some examples of these. We can try them out. So this first one is just one carbon. So if we go back to our page here, we know that one carbon is meth. It's only single bonds, so that makes it a methane. I'm writing it at the end because we know there's going to be other things in front of it. And then we've got to say how many fluorines there are. So the 4 fluorines, if we go back to the last page, fluorine was fluoro. I don't know if I spelled that right. F-L-U-O-R-O, F-L-U-O-R-O, perfect. So that's a fluoromethane, and then we've got to say how many of them there are. We don't have to say numbers because it's a methane, so there's only one carbon it can be off of. But we do need to say how many fluoros there are, and there's 4 of them. So we would use the prefixes that we see in this little table. 4 is tetra. So this would be tetra. tetrafluoromethane. Those can all be one word. I just sort of have spaces just because I separated it out, but really that is all one word, tetrafluoromethane. Okay. The next one, we've got 2 carbons. So just to see that right there. So we would go to our data booklet to find out how many 2 carbons would be. And we see that's an eth, that prefix eth. There's no double bonds, so it's going to be still an ethane. And then we've got to name all of those functional groups. There's lots of them. Let's just sort of sort them. So we've got 3 chlorides and 3 fluorides. So we're going to need to use the prefix for 3, which if we go back over here is tri. So this would be a tri. Trichloro and trifluoro. I'm only doing this because I don't have enough room. So it is actually trifluorochloro would come first. When we are in these situations, C would come before F. We do alphabetical order. So it goes trichloro, trifluoro. And we actually got to write the numbers of where those are. So we've got a trifluoros are at 1 and 2 and 2. And then the trifluoros are also at 1. 1, 1, 2. So I just put this one as 1 and this one as 2. I actually didn't. But you could do it either way, really. But this one I put as 1 and this one I put as 2. So that there's 2 fluorines off of the 1 and 1 fluorine off of the 2, and then 1 chlorine off of the 1 and 2 off of the 2. So you see where I'm getting those numbers, hopefully. So this would be 1, 2, 2 trichloro, 1, 2, 2 trifluoroethane. Between your numbers and your words, you need to put a dash. So I'm going to, just so that you can see what this proper name is and it's all its order, I'm going to erase this and write it out properly. So our chloros come before our fluoros. I'm actually going to write it 1, 1, 2 dash trichloro dash 1, 2, 2 trifluoro dash, and then it's ethane. So a pretty long one, but that's how you would write it out. I decided to put the 1, 1 with the trichloro just because chloro comes before fluoro in the alphabet, so I kept the number 1, the 2 1s that way. I don't think it matters which way you do it as long as you have them in alphabetical order. The next one is a 1 carbon chain. So only 1 carbon. So that is a methane. If you look at your page, there's no double or triple bonds. So we've got the ane ending, methane. And then there's 4 chlorines. From the last question, we know chlorines are chloro. And then how many of them? Well, there's 4 of them. So we would need a tetra. So tetrachloromethane. Here we've got quite a bit of carbons. 1, 2, 3, 4, 5, 6, 7, 8. So our 8 carbons, if we go to our sheet, is octane. There's no double bonds. Oh, there is. Just kidding. So we can't say octane, we can only say oct. We're going to have to tell them where this double bond is. So that double bond right there, we want the bonds to be at the lowest. So we're going to say 1. So by saying 1, we've said that they were numbering at 1, 2, 3, 4, 5, 6, 7, 8. Okay. So because it's a double bond, that actually becomes an octene. E-N-E. All right. So 1 octene, and then we need to say where our bromides are. If we go back to our, and maybe it's on here, I don't know if it is. Okay, so we're at the very bottom of your data booklet. It does say your halogens, so bromo would be what we say for Br. We've got 2 bromos, so that's a dibromo. And then there's a little dash in between. And before the dibromo, we need to say where those numbers are. So we see one coming off of, it's not the best picture, but I'm going to assume it's coming off of the 2, maybe the 3, definitely the 1. So this is not a great picture because see how this is in between 2 carbons? Take your pick. I'm guessing since it's farther over, it's probably with the 3. So I would write 1, 3 dash. So the bromos are at the 1 and 3. There's 2 of them, makes it dibromo 1 octene. Okay. And then the last one here, last example, we've got 2 carbons. If we go to our sheet, 2 carbons is an F. And because it's a double bond, it's an ethene. And then we've got 4 fluoros. 4, because that's in lots of the other questions, is tetra. I'm not going to have enough room here. So it's a tetrafluoroethene. We don't need to say where the fluoros are because there's only 2 possibilities and they're all filled. So we wouldn't need to say like they're at 1 and 2. All right. So that is that one. So the chlorofluorocarbons, it says synthetic organic molecules where hydrogen molecules are replaced with chlorine and fluorine are known as chlorofluorocarbons. So when all of the hydrogens are replaced with chlorines and fluorines. And an example of this is freon. This is commonly used in refrigeration and air conditioning units, and CFCs are linked to the depletion of the ozone layer. So you've probably heard that CFCs were used in refrigeration. I don't necessarily think they are today, or definitely way less. But back in the 70s, all of refrigeration was using those, and that's when they saw the biggest depletion of the ozone layer was during that time frame because of all the CFCs that they were using. So they're really not good as free-floating molecules in the atmosphere because that depletes that ozone layer, and then we know what the ozone layer is protecting us from UV radiation. It makes direct sun come into the earth. So how is ozone created? Ozone is O3. So it's oxygen in the stratosphere is exposed to UV radiation, initiating the development of O3, I think that's what it should say, not O2. Reactions between O3 and CFC. So it says UV radiation release a chlorine atom from the CFCs, so those chlorofluorocarbons that we're releasing from our refrigeration. The UV radiation basically splits off one of the chlorines, and then the chlorine with the ozone creates, it basically decomposes that ozone to become oxygen and ClO, which I believe is chlorite, but I'm really bad at those ClO ones. I think it's hypochlorite. Anyway, it creates that. There's also a natural decomposition of ozone occurring. So naturally we do decompose our ozone. We have our ozone plus our UV radiation. We'll actually break it down. So free-floating oxygen atoms react with the ClO, regenerating the free chlorine atom, allowing the cycle to continue. So whenever we have something like this floating around, it can now gather with the ClO, making ClO2, and then we can repeat the process and not ClO2. Just the oxygen floating around will go with regular oxygen. It won't make Cl2, so this oxygen will go back to here, and then that will create O3, and that'll make the cycle continue. So we're always depleting and recreating ozone all the time. So there's some questions to answer about regarding the ozone depletion in CFCs, but if they're in your booklet, then you should do them, but if not, don't worry about it. Whatever it says to do as practice questions there. Okay, that is the end for now for topic 1.